implicit differentiation. What we're looking at is when we have more than one variable. So we've been doing things like y equals sine of x. So we can find the derivative of y in terms of x. But sometimes you may have an equation where it's not as easy to just solve for a variable. So let's take a look at this one. If I asked you to find dy dx, would it be possible to solve for y here? Could you get the y by itself? Yeah, how would you do that? Okay. Yeah, either subtract over the x and divide by a negative, or just add over the y squared, and then what would you do? Square root. When you add a square root, you have to do? Okay, and so we actually get two different equations for the x, or for the y here. And so when you did your derivative, you would have a plus and minus on your derivative. So that's doable. We could solve that. What if I gave you like this one? Is it possible to solve for y here? Yeah, what would you do?
Minus x squared.
Mm-hmm. And then?
Square root.
Square root, we know we would need plus and minus. And so this one was a little uglier, but we could get the y by itself, which means we could then find the derivative. All right. What if we had a different equation? What if I said x cubed plus y cubed equals 3xy? Could you just solve for y on that one? No. I could get the y by itself if I only had the y cubed, but I also have a y on the other side. So this one is not one where I can easily just isolate the variable. Okay, so we still need to have a way of doing these derivatives, but sometimes it's not something where you can just solve. So what we can do is find the derivative from that original equation. When we do that, we still use all of our differentiation rules, so chain rule, product rule, quotient rule. But we do all the derivatives with respect to x. So what that means is when I take the derivative of an x, it's just like usual. But in general, if you took the derivative of a y, if I said like y equals 2x, okay, we know the derivative of y, we could call y prime. We could also call it dy dx. So when we do the derivative of something with a y, we have to put a dy dx with it. So anytime you have a y, you put dy dx. You may have multiple of those in a problem. But then once we do that derivative, we can then solve for the dy dx. And that is what's called implicit differentiation. So we are going to look at this problem. This is one where we could have solved for the y first and had plus and minus the square root, or we could just do this derivative. I'm trying to find the slope of the tangent line at the point 6,8. We know that the slope of a tangent line is the derivative. So if I wanted to do this derivative, the derivative of x squared is 2x. Okay, with the derivative of y squared, we do the derivative of, just like if we were doing x to a power, so the 2 comes down, y, subtract 1 from the power. But it's kind of like doing the chain rule here. What's the derivative of y? 1, but I told you every time we do a y, we have to put a dy dx. And what's the derivative of 100? See. So now, we could solve for dy dx. If we subtract over the 2x, divide by my 2y, dy dx equals negative x over y. So here's my derivative. You'll notice my derivative still has a y in it. That's okay. I asked you to find the slope of the tangent line. That's the equation for slope of the tangent line. What is the x value? 6, and my y is 8, so my slope is -3/4. So implicit differentiation allows us to find the derivative without having just y equals something. When we do that, derivative like normal, but any term that has a y in it will give a dy dx. Questions so far? Let's look at some more. So this is one that I told you we couldn't first solve for y. So implicit differentiation is the only option for this derivative. So we'll start with the left. What is the derivative of x to the third? 3x squared. Plus, what is the derivative of y to the third? 3y squared. But what else does that need? Anytime you do the derivative of a y, you have to put a dy dx with it. Equals, okay, 3xy. X and y, that's two different variables. So we have to treat this as a product rule. Product rule is the derivative of the first. Derivative of 3x is 3 times the second, which is just a y. Since I didn't do the derivative of the y, it doesn't give a dy dx. Plus the first thing, which was my 3x, times the derivative of the second. What is the derivative of y? dy dx. Everybody take a look at that and make sure you're okay before I move on. Do you understand where all my variables came from? So, we couldn't solve the original for y, but could I solve for dy dx here? Could I get the dy dx by itself? Yeah. So basically we need everything with the dy dx on one side and everything without it on the other. So if I wanted to, I could subtract over this 3y and subtract over this 3y squared dy dx. So we get 3x squared minus 3y equals 3x dy dx minus 3y squared dy dx. Now those aren't like terms, but what could you do? Take out a 3 and could also pull out dy dx, couldn't we? Okay. The 3 is everything divisible by 3? Do you just want to go ahead and divide by everything by 3 and get rid of all of those? Okay. So then we have x squared minus y equals, so if we pull out the dy dx, that's x minus y squared. So then we can divide that over. So dy dx is x squared minus y over x minus y squared. So that is my derivative. I asked for something a little more in this. I asked for the equation of the line, the tangent line, at the point 3 halves, 3 halves. So to get my slope, we have to plug in my points to the derivative. And that's just going to give me a 1. Then we have a point and we have a slope. Since I asked for the actual equation, plug into y equals mx plus b. I add that over, that'd be 6 over 2, so 3, so the y-intercept is 3. So the tangent line is y equals negative x plus 3. So this is one we would not have been able to do before today, because there's no way we could get the original one to be a y equals. Questions? So let's do a trig function. So I need the equation of the line tangent to this at the origin. So again, we're doing the equation of a tangent line. We need a point and a slope to write the equation of the line. The slope of the tangent line comes from the derivative. So to do this derivative, what do? You guys have to participate. Can we? Ideally, we would prefer to get the y by itself, but can you separate the y from the trig function? No, so we just have to jump in with our derivative. When you're looking at the left, what's the derivative of sine? Cosine. Angle stays the same, but what do we need to do? Change times derivative of the inside. Derivative of x is 1 plus the derivative of 2y. And it has to have a dy dx every time you do the derivative of a y. Equals. On the right, we have a 2x times a cosine of y. So we need to do a product. Derivative of the first, derivative of 2x is 2 times the second plus the first times the derivative of the second. Derivative of cosine is negative sine, angle stays the same, times derivative of the inside. What's the derivative of y? Okay. So, I wanted to mention something. We have two options here. Did I ever say find dy dx in this problem? No. So we could solve for dy dx like we did on the previous one, and then plug in our points to get the equation. Ultimately though, all I'm asking you to do is write the equation of the tangent line. Okay, and I know my slope is the dy dx here. Could I plug in my x and y first and then solve for dy dx? Since I never said you had to tell me what dy dx equals, that is an option, so it might make it a little bit easier here. The origin is what ordered pair?
0,
0,
0.
0. So if I plug in 0 for x and for my y, I get cosine of 0 plus 0. What is the cosine of 0? 1 times 1 plus 2 dy dx equals, over here we have 2 times the cosine of 0. So cosine of 0 is 1 times 2 is 2. What's 2 times 0 times the sine of 0 times dy dx. Yeah, anything times 0 is just 0, so that whole term drops off. So I have 1 plus 2 dy dx equals 2. Subtract my 1. Divide by 2. And dy dx is 1/2. Same thing we would have got if we first solved for the dy dx and then plugged in the 0, 0. It just saved us a lot of time to plug in first. So you have the option. You can flip those things. Now I have a point and I have a slope, so we can write the equation of our line. Y equals mx plus b. So the y-intercept is just 0. So our equation is 1/2x. Are we doing okay so far? You guys don't. I'm spending today and Monday on everything up through example 8. So that's 4 more examples. Do you want me to keep working today, or you want me to stop for today, let you do a few on your own, and then do some more together on Monday? Option 2, stop right now, let you guys do a few, and then we'll come back Monday and do some more together.
Yeah, kind of feel like Monday would give us a refresher from the weekend.
That's probably a good idea. I don't know what's going on with mine. Okay, so let's see what we're ready to do on our. I want you to do. Problem 17. We're not ready for that one yet. It will come later. We could really probably do 25 already. 27. So the ones highlighted in yellow, you're ready for now. You could really do any of those. We are not going to turn that in on Monday. So Monday, I'm going to do a few more examples, and I'm probably going to give you, I'll add in like 3 more problems, and that'll be the first chunk of homework for this section. And then the other problems will come later. So we'll probably just turn this all in at the end, but you can start now. Any of those highlighted problems, start working on those. And I will say problem number 1 asks you to do the same problem twice. Once by solving for y and then doing the derivative, and once by doing implicit differentiation. I'm only going to ask you to do the implicit differentiation. So just do your derivative, adding in the dy dx as you go, and solve for dy dx at the end. So you only have to do part A on number 1.